The cosmic silence. What the universe isn't telling us. The echo of the Big Bang, the cosmic microwave background. About 13.8 billion years ago, all matter, energy, space, and time were compressed into an incredibly dense hot point. Then suddenly, it began to expand. This expansion is what we now call the Big Bang. But don't think of it as an explosion in space. Think of it as space itself stretching, like the fabric of reality being inflated like a balloon. In the first moments, the universe was so hot and dense that nothing could exist as we know it. There were no atoms, no molecules, not even stable particles. It was a primordial soup of pure radiation, where photons, electrons, and quarks collided endlessly, unable to bind together. Light couldn't travel freely. It was constantly absorbed and re-emitted. It was like being inside an infinite opaque cloud, seeing nothing but white. This state lasted for hundreds of thousands of years. But then, something fundamental happened. Around 380,000 years after the Big Bang, the universe had expanded enough to cool down to about 3,000 Kelvin. At this temperature, electrons slowly began to be captured by protons, forming the first neutral hydrogen atoms. This process is called recombination, though it's a bit of a misnomer, since there were no atoms before this. With the formation of these neutral atoms, the universe changed forever. Light, previously trapped in an endless cycle of interactions, could finally travel freely. Photons were released, as if the walls of a dark room had been removed. And this light, this primordial flash, is still out there, traveling across the cosmos, invisible to our eyes but detectable with sensitive instruments. This is the cosmic microwave background, CMB. It is the echo of the Big Bang, the oldest image of the universe we can observe. It's like a baby picture of the cosmos, taken when it was just 380,000 years old. Today, due to the universe's expansion, this radiation has been stretched into microwaves, its wavelength so extended that its temperature has dropped to just 2.7 Kelvin, or about minus 270 degrees Celsius. But despite being faint, it's everywhere. No matter which direction you point a sensitive telescope, it's there. Wherever you are in the universe, you'll see the same radiation coming from all directions. This proves that, on large scales, the universe is homogeneous and isotropic, meaning it looks the same in every direction. The discovery of the CMB was accidental. In 1965, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were testing a microwave antenna and noticed a constant noise, a background hiss that wouldn't go away, no matter where they pointed the antenna. After ruling out all possible sources, from pigeons nesting in the dish to human interference, they realized it was something cosmic. Around the same time, a team of physicists led by Robert Dick had already predicted such radiation. When they heard about the hiss, they said, "We've been scooped." Since then, the CMB has become one of the most powerful tools in modern cosmology. Satellites like COBE, WMAP, and Planck have mapped this radiation with extreme precision, revealing tiny temperature fluctuations, density ripples, that are like seeds for galaxies. Where there was slightly more density, gravity pulled in more matter, eventually forming stars, planets, and on a small blue world, living beings. But perhaps the most astonishing thing is knowing that this signal has been here since the beginning. It traveled 13.8 billion years to reach us. And while it did, the universe evolved. Stars were born and died, galaxies collided, planets formed, and on one tiny rock, a species learned to build telescopes to listen to the echo of everything's birth. The CMB isn't just science. It's poetry. It's proof that, even in our cosmic isolation, we're connected to the very first moment of all things. It reminds us that we're made of the same stuff that lit up the universe for the first time. And yet, there are questions it doesn't answer. How did the universe begin? What existed before the Big Bang? And why, with so many stars and planets, have we still heard no one? These are the questions that come after the echo. And it's toward them that we'll journey in the next chapters. The twin paradox, when time stops being absolute. There's an idea we grow up with. Time is the same for everyone. 1 second here is 1 second everywhere in the universe. Your wristwatch ticks at the same rate as your friends on the other side of the world. This belief feels so natural that we rarely question it. But the universe has a surprise for us. In 1905, a young physicist named Albert Einstein published a theory that would forever change our understanding of the cosmos, the special theory of relativity. In it, he revealed something seemingly absurd: time is not absolute. It can pass more slowly, depending on how you move. This concept is hard to accept because it contradicts all our everyday experience. But it's real. And one of the best ways to understand it is through a famous thought experiment, the twin paradox. Imagine two identical twins, born on the same day, with the same genes, their hearts beating in perfect sync. One decides to spend his life on Earth, working, aging, living each moment as we're used to. The other makes a radical choice, to board a spacecraft capable of traveling near the speed of light, say 90%, 95%, perhaps even 99% of light speed. When that ship launches, something extraordinary begins. To those inside, everything seems normal. Their biological clocks tick forward. Days pass. Hearts beat. But from the perspective of the twin left on Earth, time inside the ship is moving slower. Much slower. According to relativity, the faster you move through space, the slower you move through time. This isn't poetry. It's mathematics. It's physics. And it has a name, time dilation. So imagine the ship travels for 10 years, from the traveler's point of view. To him, it's 10 years of experiences, memories, aging. But when he returns to Earth, he discovers that there not 10, but 50, 60, maybe even 100 years have passed. His twin brother, once the same age, is now an old man. Or already gone. While the traveler aged just 1 decade, the one who stayed lived nearly a century. And here lies the paradox. Why is it the traveler who returns younger? After all, from his perspective, it was Earth that moved away at high speed. Shouldn't the stationary twin have experienced less time? The answer lies in a crucial detail, acceleration. In special relativity, uniform motion, without acceleration, is symmetric. But in the real world, no one simply is traveling. Someone must accelerate to leave Earth, then decelerate to stop at a distant point, turn around, accelerate again on the return, and finally decelerate to land. These changes in velocity break the symmetry. The traveler feels the forces of acceleration. He changes inertial frames. He is the only one who can say, "I went and came back." Meanwhile, the twin who stayed on Earth remained in the same state of relative rest the entire time. He never accelerated, never changed direction. Therefore, he represents the privileged reference frame, and it is the traveler who experiences less elapsed time. This isn't science fiction. It's confirmed by real experiments. In the 1970s, scientists placed extremely precise atomic clocks on commercial airplanes. When the planes flew around the world, the onboard clocks were slightly behind compared to those left on the ground. The difference was tiny, nanoseconds, but real. Exactly what Einstein predicted. And this isn't just a curiosity. The GPS system in your phone depends on it. Satellites orbit Earth at high speeds and are outside the planet's strongest gravitational field. Both effects, special and general relativity, make their internal clocks run faster than those on the surface. If engineers didn't continuously adjust these clocks, GPS would be off by kilometers per day. Modern technology works only because we accept that time is flexible. Returning to the paradox, it shows us that time is not a river flowing equally for all. It's more like an elastic fabric, distorted by speed and gravity. And if we could build an even faster ship, approaching 99.9% of light speed, the dilation would be extreme. A round-trip journey to a distant star might take decades for humanity, but only months for the crew. You could depart young, visit alien worlds, and return to find your grandchild the same age as you. It's a terrifying thought. And beautiful. Because it means time isn't a cruel, inevitable master. Under certain conditions, it can be negotiable. But there's a limit. We can't go backward. We can only slow down. And so, the twin paradox stops being just a mental exercise. It becomes a window into a universe where time and space are intertwined, where nothing is fixed, and where reality is far stranger and more beautiful than we imagined. The vacuum is not empty, the quantum cauldron of nothingness. When we think of nothing, we imagine silence. Absolute darkness. An empty space with no sound, no motion, no energy. That's how the cosmic vacuum seems. A vast dark stage where stars shine in the distance, like lonely points in an infinite ocean. But modern physics has revealed a surprising truth. Nothingness does not exist. Even in the deepest reaches of interstellar space, where the density of atoms is nearly zero, the vacuum is far from inactive. It pulses. It boils. It's filled with activity, an invisible agitation arising from the very laws of quantum mechanics. This phenomenon is called quantum vacuum fluctuations. To understand it, we must let go of the classical idea of particles as solid little balls. In quantum physics, everything is described by fields. There's a field for electrons, another for photons, another for quarks. And these fields are everywhere, even in seemingly empty space. These fields are never completely still. Just as the surface of a lake may look calm from afar but is always rippling microscopically, quantum fields have a constant vibration, even when no visible particles are present. It's as if the universe has a permanent background noise. A minimum energy that never disappears, not even at absolute zero. This is the zero-point energy. It's so real it produces measurable effects. One of the most famous is the Casimir effect. Two metal plates placed extremely close together in a vacuum are pushed toward each other, not by gravity, not by electricity, but by the vacuum itself between them. This happens because, between the plates, certain quantum fluctuations are blocked, creating higher pressure on the outside. In other words, the nothing is exerting force on real objects. Another example is the Lamb shift, a tiny change in the energy spectrum of hydrogen that can only be explained by the electron's interaction with vacuum fluctuations. Without this effect, our atomic models simply wouldn't work. But perhaps the most striking case is Hawking radiation. Stephen Hawking showed that near a black hole's event horizon, the quantum vacuum can generate real particles. A pair of virtual particles, one matter, one antimatter, can spontaneously appear, and if one falls into the black hole while the other escapes, the latter becomes a real, detectable particle. It's as if the black hole is slowly evaporating, powered by the energy of the vacuum itself. This means that even what we consider the most absolute void, the space around a black hole, is teeming with possibility. And here comes an even more radical idea. The quantum vacuum might have texture. Just as the fabric of spacetime can be curved by gravity, the state of the vacuum can be altered by intense fields, optical cavities, or exotic materials. Researchers have already created quantum cavities with special properties, where the behavior of the vacuum changes depending on the direction of light, something called chiral symmetry breaking. This opens doors to future technologies, vacuum-controlled lasers, ultrasensitive sensors, materials with negative refractive index, even ways to manipulate light at the quantum level. And the boldest idea? Some scientists are investigating whether we can extract energy from the vacuum. Programs like DARPA's Arove, applications from revolutionary outcomes of vacuum engineering, are exploring whether we can modify the vacuum state to create usable energy differences, without breaking the laws of physics. It sounds like science fiction, but it's real science in progress. Because in the end, what we call vacuum is not a dead place. It's a vibrant sea of potential, where particles are born and die in fractions of a second, where forces emerge from silence, and where the very fabric of reality is constantly rearranging itself. So, nothingness isn't absence. It's the starting point of everything. Black holes and the loss of information. At the hearts of galaxies, hidden in the deepest darkness, lie the most extreme objects in the universe, black holes. They are not holes in the literal sense. Nor are they made of matter as we know it. They are regions of space where gravity is so intense that nothing can escape, not even light. That's why they're black. They emit no visible radiation. They reflect no light. They can only be detected indirectly, by their effect on the surroundings. Stars orbiting an invisible point, superheated gas disks spinning at high speed, gravitational waves produced when two black holes collide. But the mystery isn't just in what we see, it's in what we cannot see. What happens inside a black hole? And more importantly, what happens to the information of whatever falls into it? This is one of the greatest crises in modern physics, the black hole information paradox. To understand it, let's return to quantum mechanics. One of its most fundamental rules is that information is never lost. If you burn a book, the pages turn to ash, but in theory, all the data is still there, encoded in the particles of smoke, heat, and soot. With infinite technology, you could reconstruct every word. Now imagine throwing that book into a black hole. It crosses the event horizon, the point of no return, and disappears. To the outside world, it simply vanishes. Stephen Hawking discovered something disturbing. Black holes are not eternal. They slowly evaporate through a process called Hawking radiation. This process is incredibly slow. A black hole the size of our Sun would take longer to evaporate than the current age of the universe. The problem is that this radiation is random. It carries no information about what fell into the black hole. It's as if the universe were erasing important data. If the black hole evaporates completely, the book's information would be destroyed forever. This violates a fundamental law of physics. And if information can be lost, then everything we know about reality, from atoms to consciousness, could be unstable, uncertain, unpredictable. For decades, physicists have debated, does information truly vanish? Or does it somehow escape? One of the most intriguing ideas is that the information never truly enters. Instead, it gets imprinted on the surface of the event horizon, as if the black hole were a hologram. This is the cosmological holographic principle. All the information within a three-dimensional volume can be encoded on its two-dimensional surface. Another possibility is that the information leaks out slowly, embedded in Hawking radiation, in such a subtle way that it appears random, but isn't. It would be like reading a secret written in code, letter by letter, over billions of years. Some suggest the information goes elsewhere, perhaps into a baby universe, a bubble of spacetime that splits off from ours when something crosses the horizon. In this scenario, the book isn't destroyed, it's merely transferred to a new universe. But the most radical idea is accepting that gravity, as described by general relativity, must be replaced by a quantum theory of gravity, something that unites Einstein and Bohr. Theories like loop quantum gravity or string theory attempt this, and both suggest the black hole's interior isn't an infinite singularity, but a dense, dynamic region where time and space behave in unimaginable ways. In 2019, for the first time, we saw an image of what might be the outline of a black hole, the famous bright ring around a dark shadow, captured by the Event Horizon Telescope. It was a triumph of science. But that image didn't answer the central question, what lies inside? And perhaps we'll never know. Because anything that enters doesn't come back. Yet the very fact that we're asking these questions reveals something profound. We are trying to decipher the limits of reality. And the black hole, silent and unyielding, remains, guarding its secrets, challenging our understanding, reminding us that the universe is far stranger than our minds were built to imagine. The Drake equation and the Fermi paradox. Are we alone in the universe? In 1961, in a small room at the Green Bank Observatory in the United States, a group of scientists gathered to discuss one of humanity's oldest questions. Are we alone in the universe? Among them was Frank Drake, a young astronomer who had just led the first scientific attempt to detect signals from extraterrestrial life. He knew this question couldn't be answered with philosophy or guesswork alone. It needed structure, logic. And so, he wrote an equation. It wasn't a formula for calculating distances or forces. It was far more ambitious, an attempt to estimate how many technological civilizations exist in our galaxy capable of communicating with us. This is the Drake equation. It looks simple, but each term hides an abyss of mystery. N equals R times F times N times F times F times F underscore C times L. That is. R, how many stars form per year in the Milky Way? F, what fraction of those stars have planets? N, how many of those planets are habitable? F, on how many does life actually arise? F, on how many does life evolve into intelligence? F underscore C, how many of those intelligences develop communication technology? L, how long do such civilizations last? Multiply it all, and you get N, the number of civilizations we could potentially talk to. At the time, almost all values were unknown. Today, thanks to the Kepler telescope and the James Webb Space Telescope, we know much more about the early terms. We know that planets are common. Very common. Most stars have at least one. And many systems have planets in the habitable zone, where liquid water can exist. But then comes the great gap. We know Earth has life. But is it the only one? Does life emerge easily whenever conditions are right? Or is it such a rare accident that it's never happened elsewhere? If life is common, then intelligence should be too. And if intelligence is common, technological civilizations should be everywhere. We should see signs, radio waves, lasers, megastructures, probes, something. But the sky remains silent. This is the Fermi paradox. If there are so many civilizations out there, where is everybody? Enrico Fermi posed this question during a casual lunch, but it echoes to this day. If the universe is 13.8 billion years old, and our galaxy has hundreds of billions of stars. Advanced civilizations should have arisen millions, perhaps billions, of years before us. They would have had enough time to colonize the entire galaxy. And yet, nothing. There are many possible answers. Perhaps microbial life is common, but complex life is rare. Perhaps the evolution of intelligence requires a series of unlikely events: a large moon to stabilize a planet's axis, tectonic plates, oxygen in the atmosphere, mass extinctions that make room for new life forms. Or perhaps intelligence arises, but communication technology does not. A civilization might be wise, artistic, deeply conscious, and still choose not to send signals into space. Or not even realize it's possible. Another possibility is darker. Technological civilizations destroy themselves shortly after reaching that stage. Nuclear war, environmental collapse, runaway AI, the filter may lie just ahead of us. In that case, the term L, the average lifespan of a communicative civilization, would be extremely short. 1,000 years? 100? Less? If true, then the universe is filled with silent graves, planets where the flame of intelligence flickered briefly and then went out. It could also be that we're searching wrong. We use radio, but other civilizations might use neutrinos, gravitational waves, or forms of communication we haven't imagined. Maybe they're sending messages, but in a language we don't recognize as such. Or perhaps the universe is inhabited, but deliberately silent. As if there's a non-interference principle, a kind of cosmic code: do not disturb. It's a terrifying and beautiful idea at once, that we're being watched, but not yet deemed ready. In the end, the Drake equation doesn't give us an answer. It gives us a map of ignorance. It shows exactly where our knowledge ends and mystery begins. And perhaps that's the most important thing, knowing how to ask the question. Because as long as we keep looking at the sky, listening to the silence, searching for patterns among the stars, we're saying something profound. We haven't given up on finding company in the cosmos. Before the Big Bang, what was there at the beginning? When we look up at the night sky, we are looking into the past. Starlight takes years, centuries, even millennia to reach us. The farther we see, the deeper we travel in time. And when we point telescopes like the James Webb toward the farthest reaches of the observable universe, we reach a boundary, a frontier where light dissolves into a faint, reddish glow, almost imperceptible. This is the echo of the Big Bang, the cosmic microwave background, CMB, emitted about 13.8 billion years ago, when the universe was just 380,000 years old. It's the oldest image we can see, a baby picture of the cosmos. But here arises a question that challenges not only science, but language itself. And before that? What existed before the Big Bang? The first answer is simple: perhaps the question doesn't make sense at all. Because the Big Bang wasn't an explosion into space. It was the emergence of space, time, matter, and energy themselves. There was no place where it happened, no moment when it began, because time and place were born in that instant. It's like asking, what lies north of the North Pole? There is nothing. By definition, it's the end point. Yet this doesn't satisfy our curiosity. If the universe has a story, maybe it also has a prequel. And that's where the boldest theories of modern cosmology begin. One is the Big Bounce model, the idea that our universe wasn't the first. Perhaps it emerged from the collapse of a previous universe. Like a balloon deflating to near nothingness, then bursting open again in a new expansion. In this scenario, the Big Bang isn't an absolute beginning, but a turning point. A pulse in an eternal cycle of expansion and contraction. Some scientists search for traces of that prior universe hidden in the CMB, subtle patterns, like frozen ripples from a time before ours. Another even more radical possibility is that our universe is just one bubble in an eternal multiverse. In this model, known as eternal inflation, new universes constantly emerge within a larger cosmic field, each with its own physical laws. Ours would be just one among infinite others, and the Big Bang merely the moment when our bubble began to expand. There are even those who propose that time, as we know it, is an emergent illusion. Just as temperature arises from the collective motion of molecules, perhaps time emerges from deeper, quantum processes beyond our perception. In this view, there is no before or after, only an eternal block of events, and our consciousness moves through it like a candle lighting dark spots. These ideas are speculative, but not fantasy. They're built on rigorous mathematics, compatible with general relativity and attempts to unify gravity with quantum mechanics. And even if we can never directly observe what came before, we can search for indirect clues. Anomalies in the uniformity of the CMB. Broken symmetry patterns. Signatures of collisions with other universes. Because the silence of the cosmos doesn't mean absence of answers. Sometimes, it's just waiting for us to learn how to listen differently. And perhaps the deepest truth is this: we don't need to know everything to feel connected to the whole. Even without understanding the beginning, we are made of the same atoms forged in the first stars. Even without seeing beyond the cosmic horizon, we feel the echo of the universe's birth in every CMB photon passing through space. The origin may remain a mystery, but the fact that we're here, asking about it, might be the most extraordinary phenomenon of all.